We started section 7.2 on Monday, and we took a look at decimals, at place value, at some operations of addition, subtraction, multiplication, and division. And one of the things that your book doesn't do a whole lot of, it does a little bit. I don't really go to too much detail myself because students don't seem to have any difficulty with it at your level, of course, is comparisons of decimals. The reason it's on my mind right now is because that's something that my kids who are in 5th grade right now are struggling with. And the thing that I have found, this is for free, not in my notes, the thing that I have found that helps them the most is having the same number of decimal places after the decimal point. Or same number of places after the decimal point. So for example, just yesterday, they were supposed to compare these two numbers. And they both did it wrong. They're supposed to use an equal sign, a less than sign, or a greater than sign, and both of them did it incorrectly. And I don't remember which way they did it. I don't know. But as soon as I told them, remember, we want to put the same number of places after it, and they did this, then they were like, well, duh, it's equal. So that's something that, just for free for you, that seems to be a struggling point for my children right now. We're going to do some rounding things today. Oh yeah, we had talked about scientific notation last time. That's where we ended. Okay, so some estimation, some rounding ideas. So the first thing we're going to talk about is rounding specifically to the nearest, and it's like a fill in the blank. Some of your questions tell you to round, but then they don't tell you round to what, which is not exactly the most helpful thing in the world. But some of them do tell you. They'll say round to the nearest hundredths, or round to the nearest, tens, or something like that. So you're going to find the location to round to. We'll talk about what happens when they don't give you that information later on. That location, if the number after it is a 0 to 4, then you drop everything off at the end, you round down and make all those zeros. If it's a 5 to 9, then you round the next value up. We'll do these in an example in a minute. And then front-end estimation, which isn't quite as familiar to you probably, is really just rounding down. So what it does is it keeps all the values the same and it turns everything after that into zeros. So you use the first value and then you turn everything into zeros. So it always is a smaller number than what you began with. All right, so we've got a number, 203 and 651 thousandths, and we're asked to round it to specific values. And this does say round. If they want you to do that other item that I talked about, it will say front-end estimation. Okay, so you don't have to worry, which one are they asking about? It will tell you, you'll know. So rounding is like you've seen before. This says to the nearest 100. So let me first just write our number out again. And what digit is in the hundreds place? The which one? 2. The 2 at the beginning. All right, so that's the one that will stay either the 2 or it will go up to a 3. That's the only number that's going to actually be affected in that way. And then we use the next number afterwards to make the decision for if it's a 0 to 4, then the number at the beginning stays a 2 and everything else zeroes out. If the number is a 5 to a 9, the number 2 will go up to a 3 and then everything zeroes out. So what's going to happen on this one? It stays a 2, and so we end up with the number 200. All right, the next one is the nearest hundredth. It's one of those places where English is super fun and not the easiest language, right? To be very careful. So which digit is in the hundredths place? The 5, right? Yeah. Sorry, I meant to do it on the one below. My screen's all shifted. The 5. All right, so everything before the 5 stays the same. We don't manipulate that at all. So it will be 203.6 to start with. And then either the 5 will stay a 5 and everything else zeroes out, or the 5 will go up to a 6 and everything else zeroes out. And we make that decision by looking at the digit afterwards, the 1. So is this going to stay a 5 or is it going to become a 6? It's going to stay a 5. If you want to write the 0 afterwards, be my guest. If you don't want to write the 0 afterwards, then don't. It doesn't matter. And the last one of these says the nearest unit. So what does the word unit mean? It means the ones place. And what digit do we have here in the ones place? The 3. Yeah. So again, the numbers before the 3, the 2, and the 0 stay the same. And it's the numbers afterwards that are going to be affected. The number after the 3 is a 6. So is that number going to change the 3 or leave the 3 the same? It's going to change the 3, and the 3 will become a what? A 4. And again, you can put the zeros in here at the end if that keeps it clearer to you, or you can leave them off either way. All right, the next example is one where it talks about rounding in this sort of vague way. It says, use A, rounding, and B, front-end estimation to estimate the following. Then perform the computation to see how close your estimates are. So there's actually 3 things we're doing. The part that says then is almost like it's a part C, okay? Here's the deal. It just says use rounding. Like, what rounding? What are we going to round to? Well, we get to pick because it didn't tell us, okay? So I'll do it in a couple of ways just to show you what it might look like. Let's round to the tens place because that's really nice on this one if I use the tens place for rounding. So when it talks about rounding to help you compute, you have to do the rounding first and the computing afterwards. It doesn't help you if you compute everything and then round it at the end. Okay? Our goal is to do the rounding first so that the computation's easier. So if I've got the number 89 and 47 hundredths and I'm rounding to the tens, this 8 right here is the number I'm talking about. Will the 8 stay an 8 or will the 8 go up to a 9? Yeah, it'll go up to the 9 because the digit after the 8 is 0 through 9. Or sorry, it's 5 through 9. It's a 9. So this number will actually become 90. And then how about the other one? I've got a 32. It'll stay 30. That's right. The 2 will keep it at the 30 that it already is. And the goal is to subtract. So 90 minus 30 is 60. So let's say that we were like, oh no, I don't really want to round to the tens place. I want to round to the units place. Or maybe it was specifically told you that case. Let's try one of those just so you can see the difference and what it would look like. So at that point, we're looking at the 9 because that's in the units place and we're going off of the 4 next. So will it stay 89 or will the 9 round up to make it a 90? It'll stay 89. And that's an interesting one because I guess I wasn't entirely truthful in how I said it before. This is the case where if it did round up, it would affect the number in front of the 89, right? In front of the 8, it would affect, sorry, I said it wrong. The number in front of the 9, they make the 89 become a 90 because I've run out of digits. So on this one, it doesn't round up, so it stays 89. And then how about my 2 followed by the 1? That'll stay at 32. So what's 89 minus 32? 67. So interestingly enough, that's, oops, did I say it wrong? I did, I wrote it wrong, didn't I? 57. Thank you. It's a little bit lower than our first estimate, but still it's pretty close. Okay, so that's rounding depending on which place value you're doing it to. Front-end estimation. You don't have as many decisions to make when you're doing front-end estimation. That's a very nice fact about it. Again, it doesn't tell you what place to do it to, so we'll do it to the tens place, and then we'll do it to the units place, and you can see what the difference looks like. But in the tens place, that means you leave the first digit the same and you zero everything out. There's no decisions to make. You leave the first digit the same and you zero everything out, and you get 80 minus 30, which is actually 50. If you were doing front-end estimation to the units place, which is not typically the way it goes. Usually when you talk about front-end estimation, you really are using just the first digit. But if it told you to use tens place or something. So the 89 stays 89 and we zero everything else out. The 32 stays at 32 and we zero everything else out. And we would end up with 57. So with these particular values, it looks just like rounding. Okay? Because you're just zeroing everything else out behind. If we're actually doing what I've designated as part C, which is to actually do the subtraction, we have 89 and 47 hundredths minus 32 and 16 hundredths. So take a second, write that down, and we'll make sure everybody's on the same track with the right answer. right, what answer did you guys get? 57 and 31 hundredths. Is that what I'm hearing? Fabulous. And of course, all of my answers are not too far off. I mean, like, that's the whole point. Rounding is not supposed to give us drastically different answers. It's supposed to do something to make the subtraction or the addition or whatever we're working with easier, but still fairly close. All right. This is a really interesting question and a very maybe surprising conclusion. So let's take a look at what happens. This is a student who is trying to calculate 999 thousandths raised to the 10,000 on a calculator. So they plug it into the calculator. You could do the same thing. And their calculator spits them out an answer. And the answer that it tells them is 4.5173346 times 10 to the negative fifth. And in scientific notation, from what we learned last time, this is telling you it's a small number, right? Very, very small. In particular, it's going to have 4 zeros after the decimal point and then the 451 next. This is a very small number. And so the student's confused. The student wonders how it could be that a number like 999 thousandths that's so close to 1, when raised to a power, can result in a number so close to 0. Right? Because if you did the number 1 here and you raised 1 to the power 10,000, it would be 1. Yes? So how come something that's almost 1 when raised to that power 10,000 isn't still close to 1? That's what the student's asking. Do you see their question and why it feels a little funny? So I'd like for you to do an exercise with your calculator for me today. This is a fun one. So grab a calculator out. If you have a graphing one, that's great. If you don't, your scientific one will work just fine. You're just going to have to probably write more on your screen to make it work. So what I want you to do first is I want you to just take your calculator in your regular screen. If you're using anything fancy, it's not necessary. But what I want to do is to consider what happens that 0.999, that 999 thousandths, and just square it. Okay, not raise it to the power 10,000, but just square it and see what happens. Okay, so what did you get? Okay, is that what everyone has? Wonderful. First question, is that bigger or smaller than the number we started with? It's smaller. But I mean, it's still really close to the number 1, agreed? Okay, so from your calculator, wherever you are, whether it's scientific or not, this should work. I'd like for you simply to square what this number is. So just hit the square button again and hit enter. So in essence, what we've really done is it's not going to be raised to the power 2. It's actually raising it to the power 4 because we've squared it twice. But I want to know what happens when I simply just square it again. And this is still a number that's almost 1 when it's squared. What do you get? Okay, and I'm going to do just 6 decimal places. I'm sure yours is right, but we could get into some mess on my screen if I go too much further, so we'll just do 6. And like I said, so this is 0.999 squared. This is actually 0.999 to the power 4 because I've squared it twice. That's what I've gotten at this point. So again, the number's smaller, but like negligibly, right? I mean, like if you're doing money, that's not even any different amount of money, right? Because we only have 2 decimal points with our money system. And we're going to do it again. So again, from where you are, just hit square again and press enter. And when we've done that and we square the power 4, it actually becomes a power of 8, by the way, right? Because we multiply the exponents because we're squaring instead of adding the exponents. So what happens when I do this again? I mean, this is still so close to 1. Okay? We're going to do this a few more times. Same process. Square it again. What do you have next?
0.98412.
Is it like 120
Or no, it was
or 119? Okay, not a huge deal, but. And if I squared it again, this would be what power do I have now on my 0.999? It's 16. Okay, again. I promise we're not doing this the rest of the day. But we are doing it a few more times.
0.96849.
So this is the first time that you see a pretty nice change. I mean, like you can physically, you saw a change in the last step, but still not a lot. This one actually changed almost 2 whole pennies, right? What power am I at? We're at 32, right? Okay, let's do it again. What exponent am I up to? 64, that's right. We're going to do it, I think 4 more times. That's what I've got written down. $93 goes to what? What's our next step?
0.8797.
What exponent am I up to?
130.
Yeah, 128. All right, so the last one jumped about 6 cents-ish. What happens on the next time round?
0.774043.
What exponent am I up to? 256, that's right. The jump was much bigger that time, wasn't it? That was 10 whole cents. You would drive across town for 10 whole cents difference in your gas without question, wouldn't you? I would too. So let's do it 2 more times and we'll stop and we'll talk about what's going on here. Okay, so if I do it 1 more time, what do I get to?
0.599142.
What's my power? Close. 512. Yeah. All right. Make it one more tiny bit smaller. Okay. Last time for what we're doing.
0.358971.
And what exponent have I gotten to? Yeah, 1,024. We're stopping at this point, actually, because that 1,024 is about, right, if you take a look at the 1,024 compared to the 10,000 in our original question up there, we've actually hit 1,000, right? We're 1/10 of the way there, so to speak, at this point. But look at what happened to our results, except for the fact that my tiny writing has changed a little bit in the thickness. That's not what I'm talking about. It went from a number almost equal to 1 to a number almost equal to what?
0.
Yeah, I mean, like 1/3 at the point I'm at right now, right? And I'm not even halfway there. I'm 1/10 of the way there, aren't I? This is just to the number, I'm just to the power 1,024. I'm not to the power 10,000 or even close. So we've talked about this before because you guys asked a question. I think it was in this class, forgive me if I'm wrong, about what happens when we multiply with reciprocals. Was that last time that we talked about that in your group work? I'm getting a no, so that might have been my other class. So when we have a number that is smaller than 1 and we multiply it by itself, what happens, what kind of answer do we get compared to how we started with? It's always going to be smaller. Anytime we multiply by something that's smaller than 1, the answer that we get will be smaller than what we began with. Does that make sense to everybody? Now, it feels like maybe it shouldn't get there that quickly, but the reality is that when we increasingly square these things, I mean, I'm not just multiplying by 0.999 again, right? I'm doubling the error I've made every single time, so to speak, or the change I've made every single time. So it's something like this is what's going on. So whenever you multiply by a value less than 1, the product is smaller than the original number. And here, right, in this problem, I'll say and in this problem, we are doing this, and what I mean by doing this is we are multiplying by a number smaller than 1. I'm sorry, not 1, 10,000 times. Right, this is the whole thing. 10,000 times, I'm going to multiply by a number smaller than 1. So 10,000 times, it's going to get smaller every single time. It's not going to do it with quite the rapidness, the way that I've drawn it, because I didn't multiply by the number 0.999 again, right? I doubled it and so forth so that it would happen more quickly. It's easier to visualize. But that's what's going on. When we multiply by values that are smaller than 1, they always get smaller.